Hello students, this video is about Rutherford experiment of alpha scattering by a nucleus. So basically we are trying to study how alpha particle get scattered by using thin films. If we are using thin film, then how this alpha particle get scattered because of the nucleus present in that thin film. This was the task, and on the suggestion of Rutherford, his two associates, Geiger and Marsden, in 1911 performed this experiment on the scattering of alpha particle by the help of thin foils, and they obtained some important results for the structure of the atom from this experiment. So they are performing alpha scattering experiment. So first of all we have to know about the alpha particle. What is alpha particle? So alpha particle is basically a helium ion, or we can say a helium atom, from which both the electrons are removed. So we know that helium is 2He4, it has two electrons. So if we remove two electrons from the helium atom, that means it becomes helium plus 2. So this ion, this helium ion from which two electrons have been removed, this ion is called alpha particle. This is called alpha particle. It has a charge of plus 2e over it. So the charge on alpha particle is plus 2e, and its mass is nearly 4 times the mass of proton, because it has two protons and two neutrons is still in it. So its mass is approximately is equal to 4 times the mass of a proton. Its charge is plus 2e and mass is about 4 times of mass of proton. Now in the diagram it is shown the experimental arrangement that Geiger and Marsden use for the experiment. So the experimental arrangement is shown here in the diagram. Here we are using a radioactive source of alpha particle. It can be any radioactive source which can emit alpha particle. For example, it can be bismuth 83. It can emit alpha particles, and we will be studying the scattering of those alpha particles coming from the source. So we have a radioactive source, for example bismuth. Now this radioactive source is enclosed in a thick lead block. This is a thick lead block in which this source is enclosed, and it is provided with a narrow opening. So here is a small opening in the block from which these alpha particles can come out. When alpha particles come out of this lead block, they get collimated into a narrow beam when they pass through a narrow slit. So by passing them through a collimator or through a narrow slit, these alpha particles are collimated into narrow beam, and then this beam of alpha particles, this is the beam of alpha particles, we allow this beam to fall on a thin gold film. So in their experiment they use the gold film. This is the gold film, and alpha particles are allowed to incident on this thin gold film, and the thickness of this film is approximately is equal to 2.1 into 10 to the power 7 minus 7 meters. So this is a very thin film. Now the alpha particles, when incident on this film, they get scattered in different directions, and we observe these alpha particles by the help of a microscope. So we are using a microscope to observe these alpha particles that are getting scattered in different directions with the help of this microscope, and this microscope is rotatable. So the detector that we are using is rotatable, so that it can be rotated to detect the alpha particles in every direction. Like this, we will rotate this microscope or detector like this and detect all the alpha particles that are coming after scattering. And this detector consists of a zinc sulfide screen also. Along with the microscope, it consists of a zinc sulfide screen. So this is the whole setup of a rotatable detector. This whole setup is rotatable and is used to detect the alpha particles that get scattered at different angles. Now this whole setup is enclosed in a vacuum chamber to avoid the scattering of alpha particles by air molecules. If there are air molecules, then some alpha particles can also show scattering because of those air molecules. So to avoid that situation, we put whole apparatus into an evacuated chamber or in a vacuum chamber. Now we are using this zinc sulfide screen in the detector. The reason is when alpha particles strikes the screen, they produces tiny flash. So whenever this alpha particle hit this screen, it produces a tiny flash, and that flash or scintillation is observed by the microscope. Microscope won't be able to see alpha particle directly. It will detect that flash which was created by alpha particle when it hit this zinc sulfide screen. So that's how this whole apparatus work. Now after this experimental arrangement or the setup, let's move to the observations. What Giger and Marsden observe during this experiment and what results they put forward after that. So in Rutherford experiment, the rotatable detector here is used to detect the number of alpha particles that we are getting after scattering at different angles. Now if we plot a graph between this scattering angle theta and the number of particles scattered, we denote number of particles scattered by n theta, and if we plot a graph between this n theta and theta, then we get a curve like this. So this curve which is plotted between scattering angle and the number of particles scattered shows that the number of particles scattered decreases at larger values of theta. That means as the value of theta increases for more or the large scattering angle, the number of particles that are scattered at that angle is decreasing. So on this result, or the basis of this result, the observations that are concluded from this experiment are, first of all, mostly alpha particles straight pass honge. That means most of the alpha particles that are incident on the gold foil on the thin film, that pass straight through the foil, or they either go straight, or if they show deflection then it will be very small. So the first result is most alpha particle pass straight through the foil or show a small deflection. Okay, after that the alpha particle that are scattering at 90 degree or more is very small and is almost 1 in 8000 in this ratio. So the number of alpha particles that show scattering at 90 degree or more is about 1 in 8000, or it is very small. And those who suffer a deflection of 180 degree, the alpha particles that come back to the same path or that get rebounded means they go hit and come back, this situation is called rebounded. So such alpha particles are rare. It is an occasional case where alpha particle get rebounded from gold foil suffering a deflection of about 180 degree. So these are the three observations that are obtained from the Rutherford experiment, and the significance of this result is, since most of the particles are passing straight through the foil, so this shows that there is nothing in that space due to which that particles get scattered. So this shows that most of the space within the atom is empty. So the first thing or the first significance is, since most alpha particles go unscattered, so this implies that the space within the atom, most of the space within the atom is empty. This is the first significance. Now, second thing is, to explain large angle scattering of alpha particle, Rutherford suggests that all positive charge and the mass of the atom is concentrated in a very small region. If we compare it with Thomson's plum pudding medal, so there he said that positive charge is distributed uniformly over the sphere. But Rutherford said that all positive charge and mass of the atom is concentrated in a very small region, and that region is called nucleus at the center of the atom, right? So this is to explain large angle scattering of alpha particles. He suggested that all positive charge and mass, all positive charge and mass of the atom is concentrated in a very small region, and we call this region as nucleus, right? This is the second point. Now the third thing is, since the nucleus is surrounded by a cloud of electrons whose total negative charge is equal to the total positive charge, so the atom as a whole is electrically neutral. So the third significance is, the nucleus, that is positive charge, is surrounded by electron cloud which is negatively charged, such that the total negative charge is equal to total positive charge of nucleus. So that's why, because of this balance, that's why the atom as a whole is electrically neutral, means there is no charge on the atom, right? So these are the three significance of Rutherford experiment. This is how they prove all these facts. Other than this significance, Rutherford experiment for alpha scattering is also used to estimate nuclear size by the help of distance of closest approach. So the next thing we are going to study about is distance of closest approach. So to find distance of closest approach, we are considering an alpha particle of mass m and initial velocity v. So this is an alpha particle of mass m and initial velocity v, and it is incident on that nucleus directly towards the center of the atom, right? Means it is incident on the atom, or it is coming towards the nucleus directed towards the center or directly towards the nucleus. So this alpha particle is coming straight, or alpha particle is moving directly towards nucleus or center of the atom. Now since it is positively charged, alpha particle is positively charged, and nucleus to which this alpha particle is approaching is also positively charged. Since both are positively charged, so when this alpha particle is moving towards the nucleus, after a certain distance, when it approaches to nucleus, it starts experiencing repulsion because of similar charges, and its kinetic energy get reduced progressively, and it start converting into electrical energy. So this alpha particle is moving towards the nucleus. It has some kinetic energy, but when it come towards the nucleus and it approaches the nucleus, its kinetic energy this kinetic energy of alpha particle reduces and converted to electrical energy. Now, after a certain point or at a certain distance r naught from the nucleus, this alpha particle stops for a moment and then start coming back. Means at this point, at a certain point, its kinetic energy completely convert into electrical energy. That means at this point there is no kinetic energy, so it stops for a moment and start retracing its path like this because of the repulsion. So this distance from the nucleus, this distance from the nucleus is denoted by r naught and is called distance of closest approach. So this distance r naught at which entire kinetic energy of alpha particle is converted into electrostatic potential energy. At that point it stops and it starts retracing its path. This distance is called distance of closest approach. Now, since alpha particle when approach nucleus, it go quite near the nucleus, so we consider that this distance r naught is approximately equal to the size of the nucleus or radius of the nucleus. Means the distance that alpha particle is traveling is considerably large as compared to this distance which is near to the nucleus. That's why we consider that r naught is almost equal to the radius of the nucleus, or the order of distance of closest approach and the radius of nucleus is same. So we are finding the distance of closest approach mathematically, and that order will be similar in case of the size of nucleus also. The radius of nucleus must be smaller than r naught. From this figure we can conclude that the radius of this nucleus, it must be smaller than r naught. So by finding r naught we can get an idea about the radius of the nucleus or about the nuclear size of that atom. So to find this distance of closest approach, we have the charge on alpha particle. Charge on alpha particle is equal to plus 2e, let it be q1. Charge on that scattering nucleus, due to which scattering happen, is plus ze, let it be q2. Now z is the atomic number of gold. If you are using gold foil or if you are using any other element, then z will be the atomic number of that element of the foil of which that foil is made. So this is q2, z is the atomic number. Now the initial kinetic energy of alpha particle, let us denote it by k alpha, is equal to half mv square, because v is the initial velocity that is given, that we have already assumed, and electrostatic potential energy of alpha particle and nucleus at r naught, means at the point where whole kinetic energy is converted into electrostatic potential energy. We are going to find electrostatic potential energy at that point, and it will be equals to u is equal to k q1 q2 upon r naught. That means k 2e ze upon r naught. Right now, if we see the diagram, we are saying that at this point the kinetic energy, the total kinetic energy that alpha particle has, get converted into electrostatic potential energy. So the total energy with which it starts moving, it was half mv square. That is its kinetic energy, initial kinetic energy, it was maximum, because after it the energy is gradually decreasing only till the point of closest approach. So this whole amount of energy is converted into potential energy at the point of closest approach. So for the value of closest approach, we can equate k alpha with u as per the conservation of energy. As per the conservation of energy. Now, if we equate these two, we can find the value of R naught, K Q1 Q2 upon R naught, or this value can be written here, K 2Z E square upon R naught, and from this R naught will be 2K Z E square upon K alpha, right? 2K Z E square upon K alpha, or if we put the value of K alpha, that is half mv square, we get R naught is equal to 4k ze square upon mv square. So this is the value of distance of closest approach. Here k is equal to, this is small k is equal to 1 upon 4 pi epsilon naught, and its value is 9 into 10 to the power 9 Newton meter square per Coulomb square. So this is the value. Now Rutherford in his experiment used the alpha particles of energy 5.5 MeV, right? So this energy in case of Rutherford experiment is 5.5 MeV. So let's solve the value of R naught for Rutherford experiment. Here this is small k is equal to 9 into 10 to the power 9. Z is equal to, since we are using gold foil, so Z is equal to 79. E is equal to 1.6 into 10 to the power minus 19, and K alpha is 5.5 MeV. That means 5.5 into 1.6 into 10 to the power minus 13 joules. So substitute all these values in the formula of R naught. We can get the distance of closest approach as 2 into 6 into 10 to the power minus 19 square. This is E square upon 5.5 into 1.6 into 10 to the power minus 13. Right? So R naught is equal to 4.13 into 10 to the power minus 14 meter, or we can also write it as R naught is equal to 41.3 Fermi, right? तो 1 Fermi is equal to होता है 10 to the power minus 15 meter. 1 Fermi is equal to 10 to the power minus 15 meter, and the distance R naught is called distance of closest approach. The radius of nucleus is of the order of a Fermi, because this distance is of the order of Fermi and radius is smaller than that. So radius of nucleus has order of Fermi, right? Fermi, and 1 Fermi is equal to 10 to the power minus 15 meter. One more factor is there in Rutherford experiment. We call it as impact parameter, and it is denoted by small b. So it can be explained by the help of a diagram. So during the experiment, if an alpha particle is moving towards the nucleus like this and it gets scattered by an angle theta because of the nucleus, then if we draw a perpendicular distance, of this velocity vector, means the direction in which alpha is moving, this is the direction of its velocity vector. So if we draw a perpendicular to this velocity vector from the center of the nucleus, this is the center of the nucleus, and if we draw a perpendicular from the center to this velocity vector, then this distance is called impact parameter. So impact parameter is defined as the perpendicular distance, this is the perpendicular distance of velocity vector of alpha particle from center of nucleus. This is called impact parameter, and Rutherford from his experiment deduced a relationship between the impact parameter b and the scattering angle theta, and this relation is given as b is equal to 1 upon 4 pi epsilon naught z e square cot theta by 2 upon k, where k is the kinetic energy, or we can write b is equal to 1 upon 4 pi epsilon naught z e square cot theta by 2, and k is half m v square. So the scattering experiment give us a method to find the nature of forces involved. It gives us the impact parameter, it gives us the idea about radius of the nucleus, as well as it shows the fact that the most of the space in an atom is empty, and the positive charge and the mass of the atom is concentrated at its center, and we call it as nucleus. So that's all for the Rutherford experiment. In next video we will be studying about Rutherford postulates for the atomic model, which he gave on the basis of his experiment. So for that, stay tuned and keep studying. Thank you.